Hello and welcome guys, and this is a second video about Golang. Specifically in this video we will talk about how to process events exactly once in our application, because this is a very common scenario when you want to save something in the database, and if it happens once again, we receive this message from Kafka again, we don't want to save it again into database, right? For example, some kind of order, user activity, some kind of log, whatever it is, we want to process it exactly once. How we can achieve this using manual commits, and how we're going to do this in our application if Kafka guarantees at least once delivery by default. And spoiler alert, we're going to use some kind of database duplication ID. We will use this with Postgres, and we will have a Go routine which will run periodically and check the state of all our events that we are handling right now. And we will have an in-memory storage of these offsets and their state, right, if they are completed or not. And then once a certain batch of events is completed, we will commit them. And why is that important? Actually, let me show you an example and let's discuss what is exactly once and at least once delivery. Right, so this is the application from the previous video. So we have a Kafka topic and we are producing events. So we are receiving offset 0, 1, 2, 3, 4, etc. And we have some kind of read message loop. We are sending messages once we receive them into message channel. And once we process something from the message channel, we create a new Go routine. So we are processing asynchronously all these messages. Right, and then each message will try, each coroutine will try to save some kind of data into Postgres database. However, what is the problem here? So let's assume, as on this example, we are processing 4 coroutines in parallel, right? And the first one finished in 3 seconds. The second one finished in a second. The third one is still build process, right? It's taking 5 seconds, very long. And the fourth one got finished. So if we will commit each Kafka offset right after database operation, then offset number 4 will be ready to commit. And if we will commit it, and at the same time our application crashes, database crashes, whatever happens, we will consume on the restart from offset 4 and onwards. So offset 3 will get committed as well, right? If we are committing offset number 4 in Kafka, how it works, everything prior to that, Kafka will assume that it's done and it's not going to send it to you anymore. So message 3 will be lost forever. And yeah, if we want to have idempotent application and process everything exactly once, this is not ideal, right? First of all, we lost data. And this is problem number 1. And problem number 2 is that we want to make sure that our application processes all events exactly once, meaning that if we didn't commit any offsets at all, right, we didn't commit anything, and we will restart our application, we'll restart it, we will process event 1 once again, and it got stored into database already, we will not store it once again. So we will check if it exists in the database, and if it exists, we will just skip this event, right? And then we will, essentially we will have a state map, and we will store each offset respective and their state. If it didn't complete, we will store it as a false, and if it's completed, we will save it as true. This will run periodically based on cron, some kind of 5-second duration, and we will, well, in production, obviously you can increase this duration, but in our application we will try, I don't remember, 5 or 15 seconds, and we will check what is the state of each offset, and if it's true, we will commit the latest one, right? For example, in this example, we will commit number 1. So what might happen that we already saved something into database, but we didn't run this Go routine. We didn't commit the latest offset number 1. For example, we committed only 0, but 1 got saved into database as well. So the next time we restart our application, we will see that 1 exists in the database, already exists, and we will just commit it. We will not save it again, right? We will not be saving it. All right, I hope the visual explanation was clear. And just to clarify once again, there are other solutions to these problems. There is also Outbox pattern and CDC. And this specific solution is mostly used when we don't have control over producer. So we are just receiving events from somewhere like third-party API or within our application, but we are just a consumer. For example, we are getting some kind of logs from monitoring or activity of a user. And we want to make sure that we process them exactly once because this data can be very important. But at the same time, our focus is mostly on high throughput because we're going to be receiving a lot of this data, and that's why storing it in memory and committing like a batch of events at the same time is very efficient. So this is the solution for this specific scenario. And once again, there are other solutions like Outbox and CDC, and I will talk about them in the next video. All right, let's jump into coding and see how we can implement this. All right, guys, so we will continue exactly where we left off in the previous video. And specifically, we have, if you haven't seen the previous video, just a quick rundown. We have a producer and consumer, but you can assume that they're going to be in a separate service, like a microservice environment. One is producing, another is consuming. And actually, the approach I'm going to show you is preferably for scenario when you are just a consumer, you have no idea about producer. So essentially, we are just reacting to events, and we need to make sure that we are processing events only once. And yep, essentially, we have a ticker. We are sending messages to Kafka based on a ticker every second, right? We are producing events. And then in the main, we have we are ranging over message channel and handling the message. So the message channel is getting messages. So as you can see, we are creating consumer, right? Just default parameters, nothing special here. We have a ready channel, ready check, sorry, and we see once Kafka is ready to accept messages, our consumer, and then we just reading messages from Kafka. And every message we are sending to this message channel I just showed you in main, and once we receive it, we are running some kind of handle message function. And here, as you can see, I marked that we will have some database operation. So here we will have business logic and we will store event. How you will store them? Well, I will show you. Actually, I'm not going to be having business logic. I'm just going to be storing events. You can store, well, you will have to store them both in here. Maybe it's going to be the same table, two different tables. It's up to you. But the idea is that here we will process database operation, and after that, based on some kind of ticker duration, we will commit all these database operations into Kafka. I mean, all the events, not database operations, but once the database operation for this specific event in Kafka is completed, we will commit a whole batch. All right, that's a lot of talking. Let's start writing code, and I hope it will become more clear. All right, so let's add all the properties. And in this video, I'm going to be copy pasting some stuff from my live stream just to save some time. This video is going to be mostly just me explaining how it works instead of me typing everything from the scratch. Nevertheless, so we have message state map. Essentially, in this message state map, we will store as a key Kafka offset, which is just int64. And this is the offset we are receiving from Kafka, which are arriving in order, quite important. And then we're going to mark once it arrives as a false, so it wasn't processed. And once we complete database operation, we will mark it as true, so we know the database operation is complete. The rest, we have mutex here, right, because we will need to log them up. And this is going to be for commit duration. How often do we run our commit loop? You will see it later on. And these two, last committed and max received, this is essentially where we're going to start, from which offset we will start, and what is the maximum offset, where we'll end looping through our message state map. Right, and lastly, let's add a exit channel. This is going to be a struct as well. We will use it probably not in this video, in the next one when we're going to work with concurrency and channels once again. But for now, let's adjust our consumer. We don't need any more auto offset reset. Instead, we need to enable auto commit, and we will set it to false, meaning we will commit ourselves. It's not going to be some kind of ticker in Kafka. And then let's update our consumer with new parameters. I'm just going to copy paste the entire thing, and let's work through what we have in here. Right, so we are creating a TP variable with our topic, which we're going to use, and partition 0. And here we're using just one partition. Obviously, in reality, probably you will have more than one partition. Maybe not, maybe yes. Later on in the videos, I will show you how to handle multiple partitions. And spoiler alert, it's going to be pretty much the same, just we're going to have map of maps or array of maps. Nevertheless, let's continue with one partition. For now, let's go from simple to more complex. I don't want to overwhelm you straight away. So essentially, the next step we need to do is to get the latest offset that was committed to Kafka. And we do this by sending this TP to Kafka, right? We're creating a slice of topic partition, and we are sending the TP we just created, the topic and partition, and we're setting up a timeout of this operation, just in case if it's longer than 5 seconds, it will fail. And yeah, basically we are getting latest committed offset. We are storing it into variable, right? And then we are storing it into maximal received because this is the latest offset we received from Kafka. Essentially, this is going to be the endpoint straight away. We're setting it in the beginning. And now let's adjust here message. We will have shared message. I will add it right now. Right, we will adjust to the topic, and the rest is pretty much right. We are creating mutex. We are creating our empty state map. We are storing latest committed offset we just got. We are storing latest received, and it has the same offset right now, and how often we will check for commit operations. For now, it will be every 5 seconds. And here we need to remove subscribe because it doesn't give us control of starting commit, starting offset. Here, right, we will replace it with assign, and here we can specify the offset we want to start from. So this is going to be the latest offset we just received. The rest is pretty much the same, but now we need to add a Go routine, which will check our state of our map and commit offsets if they are all ready. But before that, I think let's create a database. So it's going to be more clear what we're going to store. So I will create a folder repo, and let me just move files as well. So we're going to have a database. Let's run go mod tidy. I'm going to use SQLX. I'm just going to walk you through what's happening here, but overall this is not a tutorial about database, and still I'm figuring out this for myself, how to use SQLX, although it doesn't seem that very complex. Nevertheless, we are creating a new database connection. Here I have some kind of random integer generation for essentially ID of our events. And here I have event repository. In event repository, we're just going to have an event ID. This is going to be our unique ID, which we'll use for deduplication. So meaning in case if the same event arrives again, we're not going to process it, right? We will check if this event already exists. Otherwise, we will store it. If it doesn't exist, otherwise, we will just skip it. Event name or event type, you can name it whatever you like. And timestamp, right? Just for convenience, just several properties. And here we have an insert operation. Nothing special, right? Just insert into database. And we have a get operation. As you can see, in both of them, we are receiving context because we can set, for example, the maximum duration of our database operation, and we're receiving transaction. And here I have as well transaction closure. Actually here we don't need it, but I just wanted to play around and I left it for you as well. Maybe you're curious as well how to handle transaction for multiple database operations. So I'm going to wrapping all these functions into this transaction closure and provide transaction into them. So as you can see, I'm receiving context, I'm receiving this repository, and I'm receiving some kind of generic function, which will accept as well context and transaction. Before that, I'm creating transaction, and I'm passing this transaction into this function, right? So as you understand, within this transaction closure, well, I will show you now. So basically, we are passing in to this function our context and transaction, and then we are returning the results, right? And on defer, we will check what happened. If we panicked, we will roll back and panic again, right? So we are catching here in recover, we are checking if our application panicked for some reason. Anyways, if it panicked, we need to roll back that transaction. In case if it was the valid error, we will roll back once again, but we will not show panic, we will just return. Otherwise, we're just committing operation, right? So essentially, we are wrapping all the database operations into transaction. We are starting transaction, and we are either rolling back or committing them. This is just FYI, a bit out of the topic of this video, but nevertheless, just wanted to share with you. Right, so the next thing we need to add types for our message. I'm just going to move it as well. So we have a message which will store metadata with Kafka topic partition. In case if you are freaking out about clean architecture and all these solid principles violated, that's not the point of this video, right? You can make this metadata some kind of generic information, right? Not specifically tied to Kafka, but for now, I'm just keeping it like so, right? You're going to be passing into a message some kind of metadata, and here we will store information about Kafka, right? If I would do it in a clean architecture way, it's not going to be tied to Kafka. Nevertheless, then we will store our event. I just show you in a repo. And what else, right? We are creating event, we are unmarshalling whatever comes in, and we are creating the event. And let me just adjust it. All right, and it works. Now let's, what is the problem? The problem is that message channel is string, but we need to adjust it to, it's going to be channel of shared message, and this should be a pointer. And now we need to adjust our read message loop. And once again, here we will create a message. And so instead of payload value, we will say that, let's call it payload, will equal to shared new message. And here we will provide metadata, which is message topic partition. And instead of data, we will provide just message. Message value, sorry. And now we will provide not string, but the entire payload. Right. The next thing, we need to update state here, right? Every time we receive the message, we need to add it into our map. For that, I will add another function. We'll create append message state. And here, as you can see, we are locking data. Once again, I can do the same with channels. We will do another video just to practice concurrency and to understand how we can do it with the channels. But nevertheless, we are locking the data. Then we are marking that this specific offset is not done. In other words, it's false. And then we are just storing the max received offset because we are receiving them in order. And I'm making copy just to avoid that we're going to override some value. So essentially here we will need to run c append message state, and here we will provide once again message topic partition like so. And I think this is all we need to do in read message loop, right? So we are appending message state and sending new type of message. Now we need to add our database operation in here. And before that, we need to add repository to our server. So here I will add event repo, gonna be pointed to repo event repository, and your server should receive it like so. And we will say event repo will be event repo. Now we are having error here. We will create database in our server. So this will be repo new DB connection. Does it return error? Probably yes. So if error, we will just panic, right? If we're unable to connect to database, it's not going to work. And here we will create event repo. This will be repo new event repo, and we need to provide our database. And now event repo we provide to our server. Okay, the next step, we need to add our database operation. So let me add it in here. This is going to be saved to DB. And let's talk about this. And actually, we're going to call it in here, right? We're going to create CTX, will be context background. We can actually add them out here, but for now, let's just keep it simple, context background, and we will call as save2db, and we will provide our context and message like so. And here message will be now pointed to shed message. All right, now let's talk about savedb function because it's quite important what we are doing here. So essentially, let's go from the inside. First, we are getting the event, checking if we have it in the database. If we don't have it, right, we are just returning from the function and skipping it, meaning that event already stored in the database and we don't want to process it once again. Otherwise, we are saving it into database. Fairly simple, nothing special here. However, let's talk first of all, do we need to get? And spoiler alert, no. The other one is, do we need to lock DB here, our table, or have higher isolation layer, higher isolation level, like serializable? I will just write sir. And because here in the transaction, if you've noticed before, I am setting it to read committed. So we can set a higher isolation level, like serializable. Why would we want to do this? So for example, if we are getting event at the same time another transaction is inserting, so we can get some kind of weird behavior when we are getting right event, and we will get here. Let's assume we don't have an event, but actually at the same time another one inserted, so we will get false here, and we will try to insert the second time basically. And the third one is, I will explain each and every one right now. Storing transaction into context, so CTX plus transaction. All right, so the first one, let's talk about, do we need to get here? And actually, no, because what we can do, we can actually store in our repo, we can make this unique, right? We can make event ID unique, and if we are getting the same event once again, we will just get an error here on the insert, and that's it, we will skip it. And this is going to be more efficient, right? Because we are not getting the entire thing from the database, and yeah, we'll just get conflict here and skip it, ignore it, or do whatever we want, basically. But why did I do it here? I wanted to play around with transactions. So essentially here, instead of get, right, I wanted to simulate. I didn't want to add another table. I was a bit lazy. But nevertheless, here will be some kind of business logic. Right, so we will store some kind of data, some whatever we want. We will do it here. And then in the same transaction, we will insert into database. And if we will get a conflict here, we will roll back the entire thing. All right, the next one, do we need to log database or set higher isolation layer? So let's think about how we're going to process the events, right? We are running handle message in a Go routine. So let's think that, for example, we are consuming events 1 to 3, and actually Go routines will process them like 3, 1, and 2, right, in different order. But anyways, doesn't matter in which order we are processing them. We are processing in each coroutine unique event ID, right? Because each event will have unique identifier, and we are processing them in different order, but doesn't matter. We're never going to process like 3 and then 333 again, right? The only time this can happen if our server crashed, but then we will consume once again all the events in the same order, right? We will consume the events which were not committed, 1, 2, 3, and then again we can consume them like 2, 3, and 1, right? But it doesn't matter to us because we are processing always only unique IDs in each save DB. So we don't need to have a higher isolation here. So read committed is more than enough, the way I see it. And lastly, context plus transaction. So here, once again, transaction closure. As you can see here, we're creating transaction and passing it like so along with context. So what can we do? We can actually set transaction inside of context, right? We will add it into context, and then we don't need to pass it out, and it's just going to be a bit clearer. But I decided to keep it like so, because I read there are some issues with adding transaction to context, but maybe I'm not aware. Nevertheless, I will explore it a bit more when I will be working with the databases, but for now, I decided to keep it very explicit so you can see the idea anyways. And yeah, I decided to keep it like so. So this can be optimized. Here, actually, the answer is no, and here probably yes. But nevertheless, that's not the point of the video. The point is how we're gonna commit now, right? Now let's move to the important part. We will mark as a completed, and then we need to add actually the cron operation. Before that, let me uncomment the get, because I didn't store event as unique in the database, but nevertheless, it should be okay. And we are getting errors with the message here as well. We need to adjust it. This can be channel shared message. Let's copy it. And here once again, this will be channel shared message and new Kafka consumer. Oh, all right. We will get it like so. Are we using it? Okay, that's very nice that we are not even using it. How was it working before? Not clear. All right. Doesn't matter. All right, now we have only mark as completed as an error. Actually, let me check transaction. I just got an idea. Okay, yeah, we don't need this part, right? We are returning res and error on error, but we are returning it anyways. And then in a transaction, we will check the error, right? So that part, we didn't need it. Okay. Let's move to append message state, and below it, let's add a mark as a complete function. And this is a very straightforward function. As you can see, we are locking our state and just setting it to true, meaning we are running it once in a defer, once the database operation is complete, we will mark it as true. The only thing that we need to think about how we're going to handle if insert failed. So if we are getting an error here, so insert didn't go through, should we mark it as a complete? Well, probably not, but for now, I'm just marking it as a complete anyways, just to not stop our cron operations. But obviously, yeah, that's debatable, and we will talk about it a bit later. But for now, let's add the most important function, the commit offset loop. And let's talk about it, how it's going to work. So essentially, we are creating a ticker with our commit duration. If you recall, in the beginning, I set it to 5 seconds. Where is it? Right, 5 seconds. And then on every tick hit, we are locking our state. And here we're just doing some validation, just making sure that we have max received. If we don't have it, we are skipping. That last committed is not greater than the max received, otherwise it's going to fail. And that last committed, if it's the same as the max received, we're going to skip once again. And then here we are essentially just mapping over our state. And we are looking for all events that are completed. So we are checking if event is true and it exists. If it doesn't exist, this should probably never happen. But anyways, I added just a security guard, essentially. We are skipping. If it's completed, we will remove it from the map. We know we are just doing cleanup straight away. And we will continue. And once we hit non-completed, so once we hit the first false, we will store last committed as offset and break out of the loop. And after that, we have one more validation just to make sure that we are not trying to commit the same offset that was previously. And after that, we are making the network request to commit the offset. And because of that, we unlocked before, so we don't hold the state locked for this entire network operation duration. And let's talk one more time what's going to happen in the loop. So let's assume we will be receiving messages 1, 2, 3, 4, and I think that's enough. And let's assume that the first one completed, the second one completed, and on the third one is false, and the fourth one is true, right? The third one, the database operation didn't finish. So the first one will get continue here, and we will remove it from our map. The second one will hit here as well. And on the third one, so here will be n equals 3, and we will set it to our last committed offset, and we will commit to the Kafka. But actually, the third one, we should not commit it, right? Because it didn't finish, so why we do it? And in Kafka, well, actually, when we are committing like third offset here, it will commit all events before that, not the one actually we are committing. So this one will be committed, this one will be committed, and this one not, this one not. So essentially, we are committing n plus 1, right? Not the one we want to commit, but one ahead. And that's why later on here, last committed, I'm marking actually the one we have minus 1. So I'm decrementing it back. I'm returning it to the second one, right, in this example. And if, for example, we've committed here, right, and after that our server crashed, and we restarted it, and we will replay messages, we will get third event as the first one, right? So we will replay from third, fourth, fifth, sixth, and so forth, right? You got the point. Well, I hope it was clear, because it might be a bit confusing, and I got myself stuck for a bit with that. But nevertheless, let's move further. So we are setting last committed to the one before that, because we will process from the third and onwards after that. Yep, here I'm just mapping over our state. This is just for printing, just to see how it's going to look after each commit, just to make sure that it's correct. And pretty much we are done with the core logic. So this is the main function, and we just need to add it into our logic that we are using it. And we will run it just before everything else. And this is pretty much it. So once again, we are handling all our database operations. Here will be some kind of business logic. We can remove get, and then we are marking it as a complete. And everything will be marked as a complete, will be checked in our commit offset loop. And on the ticker, every 5 seconds, probably in production or whatever, you will send it way higher, because we don't need to commit it that often, and we don't need to lock state that often. Well, it depends. Nevertheless, we are looping over our map and checking, we are looking for the first false. And if it moved ahead, right, we passed all the validations, we are committing it, all the events in a batch by doing one network operation. And this is pretty much the core idea. Now let's test it out and make sure that it's actually working. Right, let me start our Kafka. While it is starting, let's add table into database. I have already database running, and I'm using Debezium to create everything. Let me create a brand new database. Let's name it like Kafka YT, something like this. And we will create table events. How do I name it? Event name or event type? Okay, let me rename this actually to event name. So it's going to be event name here, event name here. Let's add it. Oh, I'm connected to the wrong database. Let's refresh it. Connect to the database Kafka. All right, and here I'm setting up event ID as primary key, so it will be non-null straight away, right? And it will be unique. So pretty much the get is not required right away, but if you will be storing event ID, like some kind of deduplication ID inside of another table, you will need to set it unique, probably. So later on in this logic, right, we can remove get. But for now, I'm just keeping it in here just to practice with transactions, make sure that it's all working all together. And yeah, but essentially we can remove this part and just add here check that if we got a violation of unique constraint, we can ignore it. It's going to be essentially will follow the same check we are doing here. And lastly, let's adjust our database. So here is the connection string. Obviously, we have localhost, we have port, the default one. I have user set to user and password to pass. And you will need to create your own if you don't have here. And here I will just change to Kafka YT. And this should work. All right, so Kafka is running. And let me check what we have in makefile. It just makeup. Let's run it and see how it's going to work. So we created topic successfully created, and we got an error unmarshalling event. Okay, I know the problem. So the issue is that probably we are producing just string. Yeah, I forgot to adjust it. So we should produce not string, we should produce new event. Did I not create it? Oh, it's repo. Share repo, new event, like so. And produce will take repo event. Actually, this will take bytes straight away. Slice of byte. Here we will need to get the bytes. So bytes error will be JSON, and we will marshal it, our message. If we are getting error, we will return. Once again, we can just panic here, right? Unable to marshal. Marshal JSON, and here we'll provide bytes, like so. Do we need T? Probably we no longer need it. We don't need an index, and we don't need this part. All right, looks good to me. All right, let's try this one more time. And now we're getting topic already exists, which is good. And as you can see, we are publishing events. Okay, let me stop it straight away. So delivered message, starting DB operation, right? Error insert, timestamp of relation doesn't exist. Oh yeah, and I remember that I removed the timestamp because it's a keyword in Postgres. So let's remove it and rename it to created. How did I name it in database? Created, right? Yeah, created. Let's rename timestamp to created as well. So they are all the same. All right, let's try this one more time. All right, now everything seems good. All right, let me stop it one more time. All right, let's look at it one more time. So starting position, as you can see, we started from offset 5, and probably this is not very clear. Let me add debuggers all over the place, and we will go through the code. And let's restart Kafka, so we start from the beginning without any errors this time. Let's down it, and let's up it one more time. Let's produce events not that often. Let's do this every 2 seconds, and let's add some kind of random processing time for our save to DB. So let's say some kind of random value will be rand int n, and let's say 5, and we will get a random number of 5, and we will slip time duration of our random, and let's do this +1, so we have at least 1 second, like so. So we will sleep for random duration from 1 to 6 seconds, right? And we will produce messages every 2 seconds. And the main important part here gonna be probably here in consumer. So let's add debugger in when we're marking message that it's ready. Let's see which commit we are starting from. What else in here? And probably our loop. The rest we've already seen in the previous video. Let's place a debugger here, and we will watch which messages we are committing to Kafka. And thinking about it now, I realized that we also need to adjust. There will be an error when we are just starting Kafka from the beginning, so we will not have any committed offset. We should say that the latest committed should be Kafka beginning, offset beginning. And if committed not equals to Kafka offset invalid, I think. Well, I'm not sure. Then we will override it and set to this value, committed dot offset. Oh, committed 0 offset. And we need to add if len if we received something. And like so. So essentially, if we starting brand new partition and topic, right, we will have no committed offsets, and we should start it from the beginning. Otherwise, we will be starting from the latest committed. All right, and actually, let's increase a bit commit duration for like 15 seconds for the first run. And in the main, let's produce messages also not that often. Where is it? Produce message. Let's make it 5 seconds so we can see the first time what is actually happening. All right, let's start our debugger and see what's happening. All right, so the first one, as you can see, latest committed. We received Kafka offset beginning -2. So if it's -2, meaning we are starting from the very beginning, because this check failed and we never overrode. Obviously, in our Kafka right now, we have no offsets committed. Let me place debugger. Oh, it's already here. That we don't have any errors, right? We are assigning our consumer to the latest offset, which is -2, meaning from the beginning, we didn't get any errors. As you can see, all good. Now let's see what's gonna happen afterwards. All right, we are trying to get event from the database. Obviously, we didn't get anything, so now we will be saving event to the database. And actually, let me place debugger breakpoint as well in our database event repo in transaction closure. Just I want to see that we are actually committing this offset. So we got already into our commit offset loop because I was stuck for a bit for quite a while. And now we got offset 0, and basically we will not commit anything here because there is nothing to commit. And we are returning from the save operation. So now we should be marking for completion our offset number 0. Right, offset 0 got finished. Let's jump ahead. And now let me place, okay, debugger is already here. All right, because it's in a coroutine, it's jumping all over the place, so it's hard to understand. Let's have a look. That event, we got no event, and this was message for offset number 4 already. So as you can see, we already produced five events. All right, let's jump ahead for a bit and see what's gonna happen. All right, which offset are we committing? Number 1. All right, which is good. No error. We are committing transaction. And yeah, I don't know which transaction we are committing, but we saved something into database. And obviously we are just, let me see, that the cron committed only offset number 0. So if we will restart right now, we should get everything from 1 and onwards. Let's do this. And we already saved some operations into database. So as you can see, latest commit got 1. So we are starting from offset number 1. We don't need debugger here anymore. Let's just make sure that we don't have any errors. We don't have any errors. So we are consuming from number 1 now. And now some events should be already stored in the database. Which one is it? Offset number 8. Probably 8 didn't get stored. Is this event in the database? All right, and we got some event already stored in the database. Which offset is that? Offset number 2. All right, so as you can see, we are not processing the same event again. Right? We are checking that it's already in the database, and now we're going to be just skipping. You got the point, I think. So now let's just allow our code to run. We'll just watch what's happening. So for now, as you can see, everything is working as expected. If we are stopping our application, it restarts from the latest committed offset. And if something already saved in the database, we do not process it once again. So we achieved exactly once processing, but Kafka is delivering at least once. So thanks to the database and to the way we are consuming messages from the Kafka, we are processing all events exactly once. Right, let me stop the debugger and let's have a look one more time what's happening in the database. So as you can see, we were marking for completion certain events once they were done. And since it's running in the coroutines, right, sometimes, as you can see, we mark for completion number 19, number 20, but probably when the coroutine for checks of our state was running, it was still not marked as a completed. So we are committing offset number 19, and then if we will restart now, we should get offset number 20. It should be stored in a database. Well, I should have stored offsets in the database as well, so we can query them, but nevertheless, if I'll restart right now, we should be consuming from 12 20 and onwards. And as you can see, 20, 21, and 22 all got marked for completion. So we should, okay, let's run it one more time. So all of those offsets should be already stored in the database. So as you can see, we are starting from offset number 20. We don't have any errors. Let's remove debugger here. Starting DB operation for offset number 20. And as you can see, right, offset 2022 already exists. Already offset 21 already exists. Offset 20 already exists, right? And now we're saving 23, 24, and onwards. Well, all right. I think this is the core idea of this video. I think I'm going to be wrapping it up for today. But nevertheless, there are still some things to improve, right? For example, when do we mark is completed? For example, if insert here will fail, right? Should we mark it for completion? Probably not. In this case, I think we should extend our state and not just mark it false or true. We should have more states like processing, completed, and errored, or maybe even more. And then if it errored, we can store it into some kind of dead letter queue and process it separately. Well, it's up to you. Probably I will do it in next videos, but for now we're just marking everything for completion. Otherwise it will block our commit loop. And also, yeah, we can remove this part. We can add some business logic and play around with it. And another part that, yeah, we can store transaction into context, but this is regarding databases. Once again, I will probably do it a bit later. And lastly, we can do it with channels instead of locks. Instead of locking everywhere like this. I don't know how performant is that, but probably we'll do it in another video as well. So there are improvements to this logic, but the core idea is working, right? So we are processing all events exactly once. All right. I think this is it for this video. Thank you very much for watching. I'll see you next time.